So this being a GERAD meet a GERAD researcher seminar. So I'm going to have one slide on my research activities in general. I work on decision making and control for multi-agent systems. So that means we design distributed estimation and control algorithms for these multi-agent systems. The agents can be either engineered, like robots, or even humans. And also we look also at, we also try to address some privacy and security issues in these distributed systems. And in terms of application, my group focuses mostly on problems arising in mobile robotics, but we also look at problems related to intelligence infrastructure systems like energy or transportation systems. So, so that was for the general overview of my research group. Today, I'm going to talk about a problem for a small team of just one human and one automated agent. And the starting point is that it's obviously, it's pretty clear that today the automated decision systems with the progress in AI are becoming increasingly capable in when they're designed on their own. However, in many systems, they need to operate as teammates with human operators. So it could be because of legal reasons that the person doing who is doing the decision has to be a human supervisor. But it can also be just because of the fact that when you have a decision to make for a specific problem, the humans can have specific information or context or perspectives that that is not coded in the machine. And so, as a team, typically you would expect that the machine, the decision support system, plus the human operator would do a better job as the machine by itself. But the question is, how do you optimize team performance in this kind of mixed teams? And so, among the questions, you have questions about task allocation, how to make decisions jointly between humans and automation. The adaptation, who makes the decisions can also vary over time, depending on the state of the human, who could be fatigued or have attention that changes over time. And so more generally, also, you want to kind of try to figure out how to design the interactions between the machine and the human. So these are broad questions that people in many different fields have asked for many decades. In decision theory for sure, but also in that's the core of human factors in psychology and so on. And also the problem is quite often these different fields hardly talk to each other. So these questions have been addressed from very different point of view. So what are some of the challenges? Well, the thing is, when we want to optimize team performance, at least in the traditional view of optimization, we typically would need a model of what we're trying to optimize, and that means here we would need some sort of model of the human performance. And the cognitive models of how humans behave are very difficult to come up with and to trust. So humans are known to have to make some shortcuts, for example. So yes, they may have some additional knowledge about a task, but they also, for example, evaluate probabilities in a way that's not completely rigorous, and so that leads to inherent biases, for example, in the decisions that they make. Also, if we want to adapt a system over time to the state of the human, there is a question of how do you characterize the state and how do you measure it? Each operator could also be different, so you have personal differences to take into account potentially. And also when we intuitively we want to formulate problems. For example, you want to say adapt the workload to you want to adapt the workload to the current capabilities of the human, the attention, the fatigue, the situational awareness. So all these are words that you want to, concepts that you want to take into account, but they are very ill-defined in the sense like it's hard to come up with quantitative definitions of all these central concepts. So these are, probably the main challenges is related to modelization. And then another thing is when you want to come up, at least in decision theory, with like broad solutions for design, but there is the thing. One thing is that the way you design the interface and the interaction between the human and the machine kind of interferes with that. In a sense, it could be that the performance is better in a certain situation, not because you somehow came up with a good way of allocating tasks, but just because you changed the interface and somehow it's changed the way the human perceives the whole task. So performance can be impacted by many different design choices, and also when you try to validate things experimentally. This also has one of the challenges, something that I mentioned before, which is it's hard, I find, to try to combine and leverage ideas from very different fields who have very different approaches. So there was a lot of work on these issues in the 80s, for example, in decentralized decision, but the view was more maybe theoretical. And then you have other fields like human factors, psychology, who take a much more empirical approach. And the challenge here is to try to combine notions from these different fields to come up with a holistic view. So, but anyways, keeping in mind these challenges, we're going to try here to focus on a specific simple problem, which I want to maybe motivate with an example of a task that we were doing experiments on. So it's going to be a problem of a human and an automation performing many binary decision tasks. And so the task that we were giving the participants in our experiments was we were simulating basically the task of a radar operator who would have to look at a screen. Okay, and so on the screen you have different objects, and so they can click on the objects, and when they click on the objects, they have different characteristics of the object appearing, and so they have to, based on the trajectory and the different information that they have to make a decision and classify the target as the object as hostile or non-hostile. And so, here we're in a situation where there are in fact quite a few tasks because they have only a very limited time to do all these classifications, and so the machine can also do some of these tasks. Okay. And maybe for the ones that are, the idea is for the tasks that are, for the objects that are easy to classify, you would want to allocate them to the human. For the ones that are more like, for the ones that are hard for the machine, you want to allocate to the human, and for the ones that are...
You know it beforehand?
What?
You know it beforehand, which object is harder?
Yeah, so that's the, like, again, the question would be, how do you figure out what's hard and okay, so we're in a situation in this case where so you can automate some of the decisions. However, you're in a situations where the human will be eventually responsible for all the decisions, and these decisions could be critical. So you don't want to kind of give to the machine's task where you know that the machine will make a mistake. And vice versa. Yeah, so in terms of applications, you can think of decision support systems for tasks like monitoring tasks, search and rescue, but also say financial trading, where you have to make many decisions, but your time constrained. Okay, so in terms of human factors involved in such tasks, the one thing that we'll be focusing on is workload. So in engineering psychology, you have this kind of notion that says, okay, a human has limited attentional resources, and as long as you're not overloading the person too much, the person doesn't have too many tasks. They have some sort of constant performance, but once you have too many tasks, they have too little time per task, and so the performance should decrease. Okay, so we have this red line after which, if you have too many tasks, basically your performance per task starts being impacted. So that's going to be one aspect of the decision making of the team optimization problem, which is that the human as a decision maker will have performance that depends on its workload, whereas the machine typically would not. And then there are other factors that you may want to take into account, for example, fatigue, which could impact the performance over time. Making decisions under stress or not. And we're going to also look at the end of the talk at trust and reliance. So trust in automation is a big topic in human factors and human automation teaming. And it relates to the fact that humans sometimes don't follow maybe the optimal policies for example, task allocation between the human and the automation because they don't naturally trust the automation. They can either under-trust, so the automation performs better as what they think, or they can over-trust as well. So sometimes they think the automation will do well, and in fact, it does not. So trust is another factor that you may want to take into account here. Okay, so we're going to formulate a problem first in a static problem where we have many different tasks and we want to kind of allocate them between the human and the automation appropriately. And then we're going to look at one quick extension to this same problem, but over time. Okay, so here is the formulation of the problem motivated by the previous scenario. So let's say we have K, so capital K tasks, this decision tasks, and these are binary decisions that you have to make for each one of them. All the tasks are available on the screen at the same time. So for example, all the objects were available for classification. And each task has a true state, which was on the example as hostile or non-hostile. So the interesting state would be H1, okay? And you may have, you have a prior typically on the, so the probability of the task being state H1 will be known, and we're gonna call that alpha 1. And so for each task, what's happening is that the automation has some data, some information, and the human also has some, okay? So now, the information that the automation and the human have could possibly be different. Okay, so we're going to call Y A K. A will be for automation and H will be for human. K will be the index identifying the task number. And so you get observations that could be in an arbitrary space here for the automation and observation for the human. There is a question about, so what constitutes observation and what kind of assumptions we make related to the observations that the automation and the human have. In doubt, we're going to assume that these observations are independent. We can discuss it offline. It's not necessarily a very good assumption, but it's not. It's sometimes motivated by the fact that the automation has no clue what the human is observing, and the human also has no clue of how the automation is working. And so the observation in particular for the human includes not just the data that the human has, but also what the human is observing in fact in that data. So it will be typically the model of the observation. So if we try to model the probability of observing something depending on the state, it will typically depend on the workload and the attention available to the human. So if I give you a large amount of data, depending on how much time you have, you will be able to spot something or not in that data, and that's part of the observation. So for the automation, because we will take the point of view of the automation, the automation will have to decide, should I take this task or not? So we're going to assume that the automation knows its own sensing model, and that's typically possible, at least empirically. We can characterize the observation model of the automation. Maybe any questions so far? So what the problem that we consider is, so as I mentioned before, because of the task load, the attentional resources of the operator are limited, and so you cannot typically give all the tasks to the operator, so you would have to choose which subset of tasks. So we're going to call N the subset of all the tasks that we're going to refer to the human. And the interface will work like this. The automation will look at all the data that it has. And after looking at all the observations for all the data, so all the information it has, it will, based on that data, decide which task it refers to the human. So which task it basically considers as too difficult for it, but also taking into account the workload that it's giving to the human by doing so. Okay, and so the other task will be taken by the automation itself. Then in the second part, we'll have a different, somewhat different interaction mechanism, but for now, we're going to assume that the automation is really referring this task and the human will take. Okay, so the question is, for this problem, if you have this batch of tasks, which one should you refer to the human? Okay, so in terms of the tools that we can use for attacking this type of problem, so there is some work on this type of problems going back to the 80s, in particular on team decision theory. So for example, a paper like Butcher et Penne was, so at the time you were looking at, say, you would have decentralized sensors which could make their own local observations, and they would have to communicate with each other to sort of somehow come up with a joint decision. What we'll not have here is this notion of communication will disappear in our problem, except for the fact that the automation will refer the task. We are not going to be having the automation design some messages for the human to help the human making decisions. We could, but it leads to more complicated problem. But these were the type of questions at the time. In a very theoretical context, if you have multiple sensors which are operating in a decentralized manner, what kind of messages should they send to each other in order to somehow come up with an optimal decision? Now, of course, there is a lot of work on this type of problems in the human factor literature. However, it's typically not trying to model things. It's typically also very application dependent, very empirical work. In terms of really trying to model decision problems, mixed decision problems, since that kind of work in the 80s, there hasn't been too much work. So there was a bit of work again in control around 2010, around 2010. But these were trying to model humans as limited, operators performing tasks, but these were not necessarily decision tasks. And so these were kind of queuing problems that people were trying to figure out, how many tasks should I send a human if we treat the human as a queue that has a kind of utilization dependent performance. And so the work that's going to be closest to us was the work by control theorists, again, Hyun, Kabamba, and GERAD around 2014, which also had this kind of setup where you would have these decision tasks you allocate to humans and automation. However, they only came up with the empirical, with a heuristic, whereas you can design the optimal algorithm in this case. And also there is quite a bit of work nowadays for the last, say something like 6-7 years in the learning literature, where people have realized that when you train, say, a classifier, if you know that the classifier will be used in conjunction with a human somewhere, for example, the human will review the decision, or the human will, maybe make some of the decisions, then you can somehow train your classifier differently so that you take into account the capabilities of the human. Okay, so in this problem, we're not gonna have any sort of learning in a sense that we're not gonna train the automated decision maker. I mean, it could be an interesting future work. The problem that this creates is, how much. So all this work has been only kind of theoretical because it's not clear how many. These days when you train a model, you need many different many examples and so the setup that they come up with, it's not very clear how long you need to train these things if you have a real human who would review all the different decisions before you get a trained model. And also there is no notion here of kind of limitation for the human in terms of workload or time constraint. So the setup is really different. So in terms of assumptions that we are going to make to solve the problem, so we're going to assume that, as I mentioned before, when the automation looks at the data, it decides to pass some task to the human. It's not going to tell anything to the human. So the human will receive the task and redo, based on its own observations, redo the classification on its own. Okay? So we're not trying to design here some sort of information message between the two. And also we're going to assume that the human is not, when the human makes the decision, it's not taking into account the fact that it received the task in the first place. So in fact, the fact that the automation transfers the task to the human conveys some information, okay? But we're kind of assuming that the human has no way of figuring out in real time what it means that it received the task, even though if it was an optimal design, we would have to take this into. And also we're going to be assuming that the human is trained, so the human is not kind of improving its performance over time. So we can talk about, say, probabilities of error on each task for the human, and it's going to be a constant. So the automation, we're going to assume the automation performance does not depend on the number of tasks that it performs, so it's the main difference with the human. Whereas the human at low workload, they should perform better than the automation in some sense. But as high workload, they should perform worse. So this is just so that there is a use for the automation and there is a use for the human. So, okay, questions? Okay, so now to go towards the solution. So in terms of notation, we're going to call, so there is a cost for each task K, if the task has a state HK and the decision for the task, so the decision will be taken either by the automation of the human, we're going to call that DK. And if H is, for example, H1 and the decision is H1, so that's correct. That's a true positive. We may have a cost which could be 0, okay? But in general, it's going to be a cost of true positive. For same thing, we could have a cost for true negative, which could be 0. Okay, so if the task is H0 and the decision is indeed H0, and then when you make a mistake, you have a false positive or a false negative, depending on if the task is H0 and you decide H1, or if the task is H1 and you decide H0. Okay, so this one will be in general positive, and this one, if you want, you can assume it will be 0. Now, I also said that we are going to know the prior probability for each task to be H0 or H1. So the automation, the first thing that it does when it receives these, when it looks at all this data for each task, it can compute the posterior for each task K. The automation can compute the posterior, the probability for the task to be in state H1, given the information that it has. So that thing is proportional to the likelihood. So we assume that we know the sensing model of the automation multiplied by the prior, and then there is a normalization constant. That doesn't matter. Okay, and so if the automation was on its own, okay, there was no human to refer the task to potentially, then what it would do is it would compute the cost of a decision, and the cost of a decision is the probability that the posterior probability that the task is in H1 multiplied by the cost of making a decision if the task is in H1, and plus the probability that the task is the posterior that the task is H0 multiplied by the cost that it's H0. Okay, so you can see that it's linear in the posterior. Okay, and so you can plot here as a function of the posterior the line for the decision H0 and the line for the decision H1. Okay, and then you would want to take the decision for each posterior for each task you can compute the posterior. So you receive a task, you observe it, you compute the posterior, you say, okay, I'm here. So which one is the smallest between H0 and H1? And I'm going to take the smallest. Okay, so in that region here left of that maximum, I'm going to decide H0, and on the right, I'm going to decide H1. Okay, so that's classical standard decision theory for the automation and so on. So the cost for the automation on its own will be the minimum of these two things, of these two lines.
Okay, can you say something more about the information? The cost of classification decisions?
This?
Yes. It's,
yes.
So what kind of?
So in the experiment that we had.
If it's coming, no problem. I can
No, I can explain. You want to know what it is in general, like an example?
I mean, you are providing some information, and this information is taken into account by, it enters the probability, right? Yeah,
so that's what the automation is sensing. Okay, so for example, the automation could have some of the data. In the example, somehow I cannot move the thing anymore. But, so typically, like for example, in our experiment, what we did was we gave some of this data to the automation, and we had a decision tree that was taking the decision based on that data. Okay, a trained decision tree. And the human had a bit more information, and also could look at the screen and decide based on it. Okay, but in general, it could be anything. So yeah, in that case, it's a bunch of tabular data that the automation has and has to make a decision based on that. Okay. Yeah, so now the thing is the automation is not doing work on its own. It has the human behind it if they want. So if the automation decides to refer a task, it's going to pay, let's say, a cost CM. We could put it to 0 because there will be an additional penalty anyways for having more workload for the human. And then from the automation point of view, it can also compute the expected cost of referring the task to the human. Okay, so how does it do that? What's the expected cost of referring to the task to the human will be if the task is H1, so you compute the posterior of the task being H1 given the automation's data. And then if it refers, it's going to pay an expected cost for the human, which is going to be the probability that the human makes a correct decision. So the probability of true positive for the human, and it's going to depend on the workload of the human, the number of tasks that I send the human, multiplied by the cost of true positive. So as I said, it could be 0. And then the probability of, so if in H1, the human could decide H0. So the probability of, I'm always confused, so of misdissection. So there was an interesting event that I referred it to the human and the human missed it. So you're going to pay the expected cost of the false negative. Okay? And you could be in the other situation where you are in fact, you're in a situation H0, the task is H0. And then you would pay, in that case, the expected human cost for making a mistake when the task is H0. So it's going to involve, in particular, the false positive. So when I refer to the human could say that there is something when there is not. But it's going to involve, you see, these probability for the human of true positive true positive and the probability of false positive for the. And so essentially this expected cost for referring depends on these two functions, okay, that we're going to assume depend on the workload. And the question is, okay, we need this thing to kind of to solve the optimization problem. So how are we going to come up with this? How are we going to figure these functions. So there could be two approaches, and in the decision theoretic literature, it would have been typically an approach based on kind of simple models, and you try to come up with analytic solutions. I think a more reasonable approach will be for us to try to calibrate things and measure these things in subset. Okay? So if you were using a first principle modeling approach for coming up with these functions, you would typically try to make a model of the human as a sensor. So you would want to have some sort of sensing model for the human, but also you will need a model of how the human is making decisions. Okay? So for example, you could assume that the human is a Gaussian sensor. Okay, so measures the tasks. If you had a very simple scenario, the task would be either 0 or 1, and then you wouldn't have some extra noise on top of that. You would have to decide if your task is 0 or 1. Subject to some noise, and the noise could increase. The Gaussian noise could increase if you have more workload. So that would be a standard kind of model in an idealized model in a decision theoretic toy problem. And then in addition to this sense, so that would be your sensing model, but you would also need some sort of model of what the human does with this and how do they make the decision. So if you were saying, okay, the human will behave as an optimal Bayes classifier, and it knows its own sensing model, then we would know, based on, again, classical decision theory, that the optimal the human would make its decision by computing its own posterior and comparing it to some threshold and deciding between H0 and H1 based on that threshold. Okay? And then based on this model of sensing and deliberation, you would come up with these. You could write down these functions that you. But there is no reason to claim that a human behaves as a Bayes classifier, and in fact, in the literature, there have been many other models proposed for decision making. So, for example, some people claim that humans behave as a softmax decision following softmax decision rules. So they would compute again their own posteriors, but then they would decide one or the other based on some probabilities that are computed based on these posteriors. So I don't want to explain all the details of that, but my only point here is to say that these models are kind of debatable. How do people behave exactly is largely maybe problem dependent and in general difficult to characterize. But anyways, so what you want, again, maybe I should have mentioned that. So what you want here is this, you want this function PT, probability of true positive and false positive for the human. This is called the receiving operator characteristic in signal detection theory. And we know that these curves characterize completely sensors. And here we're viewing the human as a sensor. And so in a sense, we're saying, because we want these functions here as a function of W for a fixed W, for a fixed workload, the probability of false positive and true positive is related and is following these curves here. And you could be for a fixed workload anywhere on that curve, depending on how the human makes decisions. So for example, how do they fix these thresholds for deciding one or the other? This threshold will move you to different points on these curves. Okay, so this curve, the one on the diagonal, is the worst. It's the function it's the performance that corresponds to somebody who just makes decisions at random all the time without even looking at the data. And as you move that way, you get better and better sensors. So in a sense, we're saying in our models, we're saying a human who is not loaded too much, who doesn't have too much to do, would be a very good sensor, would have a curve that approaches that curve, okay, with a probability of true positive that is always very high, okay, no matter the probability of false positive. And as the workload increases, most likely the human is moving that way towards a bad sensor, if you will. But how it's moving that way, how it's moving in that space depends largely on these models. And so what we're going to try to do instead of trying to model all this is just try to measure this thing, essentially measure the trajectory as W changes of these pairs PTP and PFP. And in fact, in the psychology literature, not for decision problem, but rather for much simpler problem like, you know, when I put a pilot in a cockpit, do the pilot hear the alarm or not? So there's a lot of work in psychology on this type of problems of attention. And so detection of events in environments. People have developed experimental procedures based on this signal detection theory to try to design experiments for measuring these things. And so what we did in experiments, that's essentially what we did. We ran these experiments of these radar experiments many times with different people, and we measure as a function of the number of tasks that people had. We simply measure their rate of false positive and true positive. And what we observe is somehow at the beginning, at least that's what we expect. As the number of tasks increases, the probability of true positive decreases. Okay, so you're right fewer number of times as you have more things to do, and the probability of false positive increases. Okay? However, at some point, so that's what we would expect. However, at some point in the measurements, we sort of somehow see a different behavior. So if you we would expect this guy to always increase, okay, the false positive as the number of tasks increases. In fact, we see a plateau and then it increases again. Whereas this one, the true positive, goes back up. However, the performance is still worse in that region than here, for example, because this increases faster than, this increases slower than this one increases. Okay, so but the point is coming up with a model of why these things do that is a bit it would probably be challenging. And anyways, we're going to work with these things that we're going to say are empirically characterized, and that's all we need, in fact, to complete here from the point of view of the automation this expected cost of referral. Now, if you have these curves now, okay, so that what the automation does again is compute the posteriors based on its own data for each task. It knows the performance of the human characterized by these two functions, and then we can write down now the cost for all the tasks. So the cost for all the tasks will be for the tasks. So we're going to refer the tasks called the set of tasks called N. For the task that we refer, we're going to pay the expected cost of referral, which I'm going to call gamma H. Okay, and that gamma H will depend on this posterior and on the number of tasks that we refer. Okay, so this is going to be the sum of all these terms here, which depend on the posterior, also the model of the human, and also the number of tasks that we refer, which shows up in the work. And then for the tasks that we don't refer, then we're going to pay the cost of the optimal decision of the automation by itself, which I called before C star. Okay, so in fact, this cost here we can immediately at least minimize the first part. The automation for its own task will do the optimal thing, and then we have the other tasks for which we pay the expected cost of it. Now we have to decide now how many tasks we send to the human. If we decide how many tasks we send to the human, we have also this part that depends on which task we send to the human. But our approach will be to basically decompose these two. First, we're going to kind of fix the number of tasks that we send to the human so that we have this fixed. And then for a number of tasks fixed, we're going to decide which task we would send. And then we're going to search over how many tasks should we in fact send. Okay, so we're going to solve the same problem many times for each possible number of cardinal n. And this is not a very big search. Even if you have 100 tasks, you have to solve the problem 100 times, but each problem is very simple to solve. Okay, so to figure out, to do this optimization, what we can do is rewrite first this cost as so you add and subtract C star for each task n as well. So you have a constant now, and then I have this sum here of k over n of this gamma h. That should be h. And you have this difference here appearing between the cost of the automation doing the decision on its own minus the cost of referring the task. Okay? So minimizing the total cost corresponds to maximizing this thing. And this thing involves basically the difference between just keeping the task for yourself or sending it to the. So we're going to call for each task this G index here. So there's for each task, the thing that we want to maximize involves this G index, which is again this cost reduction, this number here, is the cost reduction provided by a referral. So it could be negative if it's better to keep the task for yourself. And because we have to maximize that thing, okay, we have to maximize that sum here. Basically, what we can do is order all these indices by in decreasing order for each k, and just pick the, since we know that we have capital N to choose and capital N for now is fixed, we just pick the highest. So it's going to maximize the minimize the cost or maximize the gain. So for a given workload, the bottom line is for a given workload, it's easy to figure out which task you should refer by just ordering these indices that again depend on a workload that is for now fixed, the posteriors that the automation calculates, and also this model of performance of the human given by these true and by these ROC curves or this true and true positive and false. And now after that, we can just do an exhaustive search over the workload and come up with the optimal allocation. Okay, so again, pictorially, if we go back to the decision regions from before, what the human adds is we have the decision curves for the automation, and for a human, if you look at the expected cost of referring a task to the human, you get lines, okay, that depend on workload. For each value of workload for the human, you get a different line. So that's a line for if I load the human at W1, and if I consider a fixed workload at W1, I would refer all the tasks for which there is a positive gap here between the line and the line of the automation by itself. Okay, so if, for example, the task in these regions would not be referred, the task in these regions would be referred, and the task in these regions would not be referred. However, you also have to maintain the workload here. Okay, so if there are many tasks here that fall in these regions, I cannot refer more than W1. So you still have to order them and only pick the W1 first of these tasks, which we can do by ordering this gamma indices. Okay. So let's skip that for now. And so in simulations, so that gives us the optimal strategy of our allocation. In simulations, what we did was we also compared this to other strategies. So one interesting thing is to figure out the advantage of looking at the data before referring. And another thing is to figure out what's the impact of changing the workload, of adapting the workload. So we are comparing here to a policy which we call blind allocation, which sends a fixed number of tasks to the human at each period. I mean, a fixed number of tasks to the human. There's just one period for now. And so somehow we optimize the number of tasks that we should send. However, we are not looking at the data that we receive before sending the tasks. Okay? And there is this static allocation policy, which also sends a fixed number of tasks by solving an optimization problem, which is a bit involved. But bottom line is the number of tasks will be fixed, but we will, as in the previous, as in the optimal policy, we will look at the data before we choose which task we send. Okay? So what we observe is, it's probably not the best way of representing it, but what we observe is there is a significant gain in looking at the data before you refer it. So here, for example, we see the performance. If I take one instance of the problem, you get the performance of the blind allocation, which doesn't look at the data, essentially allocates without looking at the data. And that's the performance of the optimal policy. And very often the optimal policy, adjusting the workload based on the data, you could do without, because very often what we observe is you get almost the same performance if you were just optimizing the workload a priori, which could be useful in practice because we may not want to have like a system that sometimes gives you a lot of work and sometimes it doesn't. And also, but in any case, the advantage of knowing the optimal policy is that you can also characterize, for suboptimal policies like this static allocation, which may be desirable for operating reasons, you can characterize it its optimal. The optimal solution. Okay. Any question?
I have a long series of stupid questions. I know nothing about this problem, so my culture increased significantly in 45 minutes. So can you say it again? Who is in charge of allocating the tasks?
Yeah, so right now it's the automation. So purely the automation. And if we pass to the second part, it's a bit different.
So it seems to me that there is some relationship with what is done in discriminant analysis, for instance, in statistics. You can allocate individuals to group randomly. And this is what you get, and after that, if you have some information, you do another allocation and you see how much you improve thanks to the available information. So it's something similar going on.
So sorry, what? I'm not familiar with this.
Okay, I have a sample of individuals, and I'm a banker. I don't know if I should give you the loan or not. I can do it randomly and have some results. Or I can look at your past credit history, your age, etc., to do the allocation, and I can measure how much I improve thanks to this information. So here is this something going on in the same spirit?
Well, the difference I would say here is that I'm not allocating something. The automation is not allocating. After it's allocating the task, the human has to do something, right? So the human has to make the decision.
But in fact, what is crucial here is how it sends the task to human or not. No, because if I understood well, the human is always perfect in the sense I cannot distinguish between different things. If I have a human, I know what.
We have a model of generic human. Yeah. So we could model different humans, but we could in fact do everything. These curves, these performance curves, they could be adapted to specific humans. But here they're not.
So here we have two things. One is the referral, and after that, whether the human is making the right decision.
Right.
So,
yeah, I mean, because you see everything from the point of view of the automation, you can do everything that happens after that by the human as a fixed cost. So possibly there could be. So you're saying in that literature there is a study between. Is it better to just allocate randomly?
No, it means how much you gain in performance if you have additional information. And if you use this additional information, right? And you have threshold to send the right or to the left.
Yeah. I mean,
yeah. So here is something much more sophisticated.
But you have these type of problems also. They show up in the literature on learning that I mentioned before. Like people for these decisions that are critical. You want to know if there will be a banker making a decision, but the banker will also make a decision based on possibly some machine learning model that gives it some hints of what they should do. And so here I'm more interested, I would say, in the problem of, okay, if you have a computer that tells you you should reject the loan, what should you do? Based on, you may have extra information about the person, you may know the person as a long-time customer, so the machine maybe doesn't know all that stuff, right? So anyways, let me just say a few words, I guess, on the other part. So we also extended this problem to a dynamic setting, and incorporating a state that evolves over time. So there are different states that you can consider. One would be fatigue. And in fact, there is ongoing work with Aditya and our student Rehan on incorporating fatigue and models of fatigue. So basically, it means that performance over time will vary depending on how rested or not rested the person is. And so before we didn't have anything dynamic, but then that leads to using dynamic programming and optimal control tools. In this work that I have on the slides, the dynamic state will be a trust state. And so there are different models of trust that have been proposed in the literature. The trust impacts what's called reliance on automation. So what's happening is sometimes the human so far was receiving these tasks and just taking them. But in fact, what's happening is the humans in these situations may want to have the automation or not. Okay, so they could take some of the tasks that the automation is doing, or not want the automation to do too many tasks, or so on and so on. And it's going to depend on some sort of this cognitive state that people want to call trust. And so, so this is an example. So there are different models of trust that have been proposed. So, for example, one of them is this BFT model of trust, which is a two-state model that models trust over time, and this depends on this impacted by the cost, and the cost doesn't impact trust directly, but impacts something called belief in the capabilities of the automation and so on. We're going to use a simpler model than this. My only point is you could, it's plausible that you could make up a model of dynamics of trust. And trust, what it does, it's some sort of abstract concept that impacts reliance. Okay? Is the person, what you can observe, in fact, is the person using the automation as they should, overusing it, underusing it, and so on. Okay, so what we want to capture here is we have this recommendation of which task the human should do, and if we want to incorporate trust, somehow the trust should impact the likelihood that the human will follow the recommendation of the automation. Okay, so our extension of the model will be the following. Instead, the automation will not just refer a number of tasks, but what they will do instead is they will order all the tasks. So they will come up with an ordering of the tasks in terms of priority, and then they will send a suggested workload to the operator. Okay, so the automation will say, here should be the order of tasks. You should try to do this task in this order. And I suggest that you do these many tasks, okay, based on my model of your performance per task. And but the human could deviate from that. So we're going to assume that the human follows the list, the ordering of the list. However, they could take more or fewer tasks than suggested. So again, the automation will evaluate its data, and it's going to also measure the trust state. So this trust state here, we're going to assume that it has only two values. So it could be, normal trust or under trust. And how do you measure trust state? So in the psychology literature or human factor literature, it typically requires a long questionnaire. But what we could assume here is, let's say the human could have a switch and say, I feel confident or not about the current state of the automation, the capabilities of the automation, and just activate the switch as 0 or 1. And this switch will kind of give some indication of the human following or not the recommendation of workload of the automation. So the automation will be making a recommendation of workload that I'm going to call WR at time t. So we're going to receive batches over time, batches of tasks. Before we have just one batch. Now we receive one batch, and then the next period another batch, and so on. So the automation will be making a recommendation WR, but the human may take more or fewer tasks depending on their trust. and these fewer tasks will be called the WS, for a total task that the human takes which is called W. And we're going to assume, so for part of this work, we may have to assume a model of how the trust evolves. And in fact, typically we won't need this model, but if we want to prove certain properties of the policies, we may have to reason about how the trust evolves. Okay, so because we have a trust state, now we have also a transition function, a transition probability for the trust from a given state to the next state, and we can just look at the next state being, so there are just two states, so it's characterized by the next state being normal, and the under trust will be 1 minus this. And it's going to be depending, this transition probability will be depending on the costs, or the performance of the team at the current period. Okay, so if the team behaved well, or here you could have something that depends only just on the automation performance. Depending on how the team performed at the next period, the trust will be higher or high or normal or Okay, so what we have is I'm going to just summarize and not go through all the details of this 1 or 2 slides. What we had before, we had a simple optimization problem, okay, which was ordering these gamma indices and picking the highest ones. What we have here, because of that uncertainty in the number of tasks that the human takes, we have some sort of expectation of the sum to maximize, and before we didn't have this expectation. So this is a bit more complicated. And it depends, in fact, to find the optimal solution, we need to have some information about the distribution of this extra task that the human takes, depending on their trust state. Okay? But we can show that this problem remains tractable if we have this information about the distribution of extra tasks, and it can be solved efficiently as a linear assignment problem. So this linear assignment will be giving me, at least for each for each suggested workload, the ordering of tasks that I should provide. And then I can also do an exhaustive search over the different suggested workloads to cover the final optimal solution. Okay. And then the last part is, so that's what we can call the greedy policy here, which is basically just looking at the task at the current period, and not trying to optimize as an optimal control problem over all the periods. It's just trying to figure out the best list and the best ordering of tasks and the best suggested workload for the current period. But of course, what you do at period T has an impact on the trust state. Okay. However, the situation here is a bit is the following. Typically, if the automation would perform the best it can at the current period, we would expect that it's going to have a positive impact on trust. So behaving greedily, okay, optimizing the current period should be optimal in many situations, okay, of interest. So we try to prove, in fact, that this myopic policy, trying to just do the best for the current period, under which conditions on this, for example, transition probabilities and so on, is it just the optimal thing to do? Okay? And it's very advantageous to do that, to have these conditions, because for this, you don't need, first of all, to solve an optimal control problem. And the dynamic program, when you have to solve it, involves these transition probabilities that you then have to characterize and so on. And so just going through this, just here, the idea is if for example, being able to minimize cost gives me a higher chance of staying in the normal trust, as we would expect. Also, another condition that we want to capture is if if normal trust gives me a response from the human that is more predictable. Okay, the human has to follow the trust, to follow the recommendation more if it's in a high trust than in a low trust. Then somehow I would like to prove that the myopic policy is okay. And so we could in fact prove this under this, so make these conditions a bit more technical and precise. However, there is one thing that we had to introduce, an assumption that we had to introduce to prove that this myopic policy is optimal, which is that somehow the transition probability, so the probability of transitioning to the normal state should decrease with cost. That's so as the cost increases, we should be trusting less the system. However, we had to enforce that this decrease in cost had to be linear in cost. And this is related to the fact that when we do dynamic programming, at least classical dynamic programming, we optimize over the expected cost. But here somehow, potentially if the policy behaves well for expected cost, but doesn't behave well for, say, the variability of the cost, the risk, if you will, then potentially it could be this kind of intuitive solution here that the myopic policy is optimal could potentially not be optimal. So, but anyways, under some technical condition, we can prove that the optimal policy is optimal. So let me conclude here. So this is just saying that yes, it's useful if you have a state, a trust state. It's useful to take into account versus not taking into account. So anyways, conclusions. So we have for this kind of, even though it's a simple scenario and simple problem, we can come up with some principles guiding how the automation should decide which task to send to the human or not, and how to optimize team performance. As I mentioned, automation may need to adapt to other operator states, not just trust, but for example, fatigue and so on. So we have ongoing work on extending this framework to other scenarios. Some of these states, like trust, I was assuming here that I could observe it, but in many cases you can't. So you have to measure it somehow, or measure something about the state, and leading to partially observed models where inference about the state is typically very noisy. Other things you may want to do is adapt the decision, adapt the automation, the model of performance of adapt the automation itself to the operator. So the operator, when it makes a decision, for example, gives some feedback to the automation on how it should behave. We're doing we have some experimental results that on these kind of setups where we want to also extract some more ideas for extensions. And you can come up with many different types of refined models of these things. So for example, one thing that we didn't model here is the different impact of false alarm versus misdetection of automation. So when you have an automation that makes decisions like that, or classifications, or raises alarms, if it misses something, for example, then very often for the operator, then it means you don't see anything. Whereas if the alarm is raised when there is nothing, okay, so you have a false detection, then after a while the person gets irritated, because you have all these false alarms, and sort of starts using the system less. Okay, so the different types of errors that the automation can make also has an impact somehow on the reliance of the human on the automation. Okay, so these are kind of examples of extensions that one can pursue in this technical. And I think that's it. So yeah, thank you.
Thank you, Jérôme.